All right, we're continuing with homework problems for 4.8, and this is going to take some struggling with your calculator. The point here is that your calculator doesn't always speed up a problem. So if you have not practiced, it's going to take you a long time to do problems on tests or quizzes. So though I'm showing you the answers right now, please pause the video, try the problem yourself honestly, and then come back and see if your work agrees with mine. But let me give you some tips along the way here. So in our first rational function, don't be so quick to just go to your calculator. Do you notice how much you already know about this function? The degree of the numerator and denominator are equal, so it has a horizontal asymptote at 1. Y equals 1. It says when Bob looked at his calculator graph, he thought that the asymptote was at the axis because, of course, the line y equals 1 could look very close to the line y equals 0. So you have to be thinking as well. Notice the numerator and denominator are factorable, so we can find the x-intercepts. Those would be the places where the numerator is 0. The y-intercept, there is none. Is there any place where if we put 0 in for x, we would get negative 6 over 0? So undefined, so there's no y-intercept. Vertical asymptote, well, we just decided that division by 0, there are two vertical asymptotes, and the horizontal asymptote from the ratio of the leading coefficients. All right, so you know a lot about this function before you start. All right, if you haven't already, pause and go to your calculator, find the first derivative and paste it into y2, and it should look like this value. So notice that right away we see two critical numbers. 0 and 1 cause the first derivative to be undefined. So now if you go to the home screen or to the graph screen and find out where is the first derivative equal to 0, that would be when the numerator is equal to 0. And not surprisingly, you could do that by quadratic formula also. So you should come up with two different places where the first derivative is 0 and two places where the first derivative is undefined. So do you see four critical numbers? And now we want to test the intervals to find out if f is increasing or decreasing. So when we have four critical numbers, do you see that we have 5 different intervals to test? So you could use a table on your calculator, or you could just test in the home screen, or you could look at a graph. So multiple different ways, but you want to find out what do you know about the first derivative in each of these 5 intervals. And notice that there's a vertical asymptote here. This is not going to be a local max or min. This is a vertical asymptote. And at positive 1, this is a vertical asymptote. So it's going to rise to positive infinity or fall to negative infinity next to a vertical asymptote. So there's not going to be extrema, but it's still important. So between these two values, f is decreasing since it's negative. Then it's decreasing again on the other side of the asymptote. And then it has a local minimum because it changes from decreasing to increasing. And then we have a vertical asymptote. It's increasing on both sides. It's increasing on both sides of that vertical asymptote. So can you already try to picture what the graph will look like? And then in this interval, the first derivative is negative, so it's decreasing. And this is a point of continuity, and it changes from increasing to decreasing. So by the first derivative test, we know that f has a local maximum at this value. All right, so now we can answer the next question. And to find the y-coordinates, and notice I wrote them in exact form. You could also do green diamond enter. But you're simply going to say, what is y1 of 3 plus the square root of 6? Find the y-coordinate at 3 plus the square root of 6 on your original function, not on your derivative. There's your local maximum, and here's your local minimum. at 3 minus the square root of 6. All right, so next let's work with the second derivative. So now pause if you haven't done this already. Pause and go and find the second derivative and paste it into y3. And then I've written it here for you. And notice the second derivative, now we don't call them critical numbers, but the second derivative is equal to 0 at two different places. The second derivative, excuse me, the second derivative is equal to 0, or is undefined when the denominator equals 0. The first derivative is equal to 0. You can either do this graphically, or you can now go to the home screen and solve for when is the numerator equal to 0. And that would be at approximately 7.910. So notice we have three different places. So again, for the second derivative, where does it equal 0? Where is it undefined? We don't call them critical numbers, but we do exactly the same thing when we test for concavity. So 3 numbers divides the real number line into 4 different intervals. So you're going to test a value, and you don't have to show this on paper the same way that I did, but you need to either use a table, an ask table, or use your home screen or a graph to find out in this interval, what do you know about the second derivative? It is less than 0. And then we have a vertical asymptote, so there's no point of inflection here because it's a discontinuity at a vertical asymptote. And then if you choose a number between 0 and 1, the second derivative is positive. So now we've switched from concave down to concave up when we crossed over the vertical asymptote. And now when we cross over the next vertical asymptote, now the graph is concave down. And now at 0.7910, we have a negative second derivative changing to a positive. So this is the only continuous point. This is a point of continuity where concavity changes. So we have one inflection point. All right, why do we care about all of this? Well, there is no way that you would have come up with this graph if we didn't have all of that information. So now, if you want to do this graph on your calculator, you are going to have to zoom in on each part separately, because will you understand that this section stays below the horizontal asymptote? This place, it rises up to a maximum and then comes down above the asymptote. So remember that we can cross a horizontal asymptote. A graph simply can never cross a vertical asymptote. And on your graph, this parabola is hanging way up here. This is bigger than 20. So here you'd have to find the coordinates here of the local minimum, remember? 11 plus 4 square root of 6. Well, that might be easier if you did green diamond enter to approximate that. So you might have to do a completely separate window to zoom in and find this section. I've seen many students graph only these outside 2 branches as if there was a gap in the graph. But between these 2 asymptotes, you have to figure out where does the graph go, and it's way up here. So this graph isn't really drawn to scale. All right, so it takes a lot of work. If you read my answer first and you didn't try that problem, in a day or 2, come back and try it again. All right, let's try another one. So the point here is when we have functions we're not so familiar with. So this one we can't even call a rational function because it's not a polynomial to a polynomial. All right, so what do we know? Well, this one has a domain issue. We can't put negatives under the square root. So right off the bat, think about the domain here. We can only pick values from 0 to infinity. So we can ignore everything smaller than 0. All right, so the same idea on your calculator. Find f prime of x and paste it into y2. And you can do these problems in any order that you want to. So you could also immediately find the second derivative and paste it into y3. And when you see these in pretty print on your calculator, you might notice some values that are undefined. All right, so critical numbers, you want to use your solver and say when is the first derivative equal to 0, and then set your denominator to 0. So notice that it is undefined when x is equal to 0, and it is undefined when the numerator or denominator is equal to 0. So you could set the numerator to 0 and solve it in your home screen. You could set this factor to 0 in your solver. So instead of calling it solving y2 is equal to 0, you could just type this equation. So you could solve x squared plus x plus 1 quantity squared. But do you really need to solve this? Can you guys see that this is never going to be equal to 0? Because we're squaring a number. We're squaring a number, so this one could never be equal to 0. I think I'm saying that correctly. You would test that out to make sure I'm correct, but it looks like it's always going to be positive. All right, let's see then. In our second derivative, you can set the numerator equal to 0. And you can find out when is it undefined. That you can do by setting the denominator equal to 0. And then we can start testing intervals. So unlike the showing you the intervals like I did on the previous problem, you can just pick a number in each of the intervals and then do your justification all at the same time. So remember that we have 3 different critical numbers. Here I've approximated them. So the negative 0.767 up to 0, and then the 0 up to 0.434, and then the 0.434 to infinity. So you want to test all of those intervals. Okay, so, and we don't care about the negative side. The part that is less than 0 is not in the domain. So I actually don't even need to worry about that one because the original function is undefined when x is negative. So we use the domain of the original function, not the domain of the other two. All right, so once we've answered increasing and decreasing, where it changes from increasing to decreasing, we can find out a local maximum. And how can I say it's a global maximum? Well, if the graph only increases and then it only decreases, like a parabola, like an inverted parabola, if it only increases on one half and then it only decreases on the other side, doesn't the local maximum have to be the global maximum? All right, and then our second derivative, let's test for concavity. So we want to test the intervals, and again, remember we don't care about this negative interval because it's not in the domain. So we only have to test between 0 and 0.9371, and then from 0.9371 to infinity. And sure enough, the second derivative changes sign. So we've located an inflection point. So our graph is concave down and then concave up. And then for sketching our graph, make sure that you make it clear what window you choose. You don't have to use the same window. I made a note here that I like to see the x and the y axis. So instead of starting exactly at 0, I always start a little bit smaller than 0. But it certainly would be fine. Here's another way of showing your window, and you could have just started at 0 to show the graph. But notice what we found out. We found out that it increases and then decreases. We found out that it was concave down and then it was concave up. So the graph appears to match all of the information that we've discovered about it. So while it might take you quite a while to do each of these problems, every time you do one of them, it will go faster and faster. And on a test question, you might not have to answer every bit of this. You might be asked a question simply about concavity, or you might be asked a question about global minima. So you might not have to do all of these parts in every problem. But taking apart a complete equation using its first and second derivative is really one of the most important applications of calculus. So practice using that calculator.